Good morning, all. It's an absolute pleasure to be here at the summit and to be presenting on behalf of our founder, Dave Ditzel, our former chief architect, Roger Espasa, who's here. Hello, Roger. And all my colleagues at Esperanto. Today, I'm going to talk about Esperanto's RISC-V extensions optimized for the machine learning inferencing applications. The talk is also going to cover a high-level view of the Esperanto supercomputer on chip version 1, aka ET-SoC1. A few of the crucial architectural and implementation choices we made for our ET-SoC1 design, which has enabled us to create one of the most energy-efficient solutions for machine learning inferencing. So Esperanto is a foundational RISC-V company, and it is at an intersection of two very important trends, machine learning and RISC-V. We have been an adopter of RISC-V from the early days and have created low-power, high-performance CPU designs, and we are leading the way and proud about it for having created one of the best solutions for machine learning inference. Using the low-power RISC-V architecture, Esperanto is pursuing technology directions to facilitate and run applications from data center to the edge for both AI as well as non-AI HPC kind of workloads. Our ET-SoC1 design is capable of processing almost all the known AI workloads at about 20 watt power. So here's a quick overview of Esperanto supercomputer on chip. You can see the silicon diagram, package part, as well as the board under bring up. So this chip is working. It is running ML code as we speak. And hopefully, in the months to come, we'll be publishing all the numbers as well. So ET-SoC1 is fabricated in TSMC 7 nanometers. And on this one 7 nanometer chip, we have put 1,088 energy-efficient ET-Minion RISC-V cores, each with its own tensor and vector unit. Each of this core is multi-threaded with 2 hardware threads for execution. Each core can operate between 0.5 gigahertz and 1.5 gigahertz. The chip also has 4 high-performance out-of-order RISC-V processors, which we call the ET-Minion. It has the PCI Gen 4 support. It can be configured to be operating at 1 by 8 lane or 2 by 4 lanes. Our chip has over 150 megabytes of on-die SRAM and up to 32 gigabytes of DRAM. The chip can be operated as a standalone processor or as an accelerator connected to any PCI interface bus to the host. We are able to operate using less than 20 watt of power on most of the AI applications. Now, before going into the details of some of the implementation architectural choices we made for our design, it's good to understand some key requirements that we learned talking to all the hyperscaler customers who run these ML workloads on their data centers. Machine learning workloads, especially the recommendation models, they have some of the most demanding performance and memory requirements and have largely, to this day, been run on the x86 servers. Now, demand for these additional performance is always growing more and more, right? For these customers, rather than having to build new data centers or buy more servers, they would like to have a way to increase the performance in their existing servers. Most of these servers have an available PCI slot where the acceleration card could be fit. But these cards now have some stringent requirements. First, the performance requirement. The performance of the accelerator card needs to be substantially higher than the x86 CPU host, which means they need to have peak compute rates anywhere between 100 to 1,000 teraops. Second, the power requirement. The accelerator card needs to fit in the existing infrastructure, which in many cases just has one PCI slot available. And this slot has a limited power budget, anywhere typically between 75 watts to 120 watts. The third is a support for different data types. Most ML inferencing can work pretty well with 8-bit integers. But talking to the customers, we learned that they would want the solutions to also support 16-bit half precision and 32-bit single precision floating point. Next is the capacity or the storage requirements. The accelerator card should have at least 100 gigabytes of DRAM. This is just because the workloads are becoming more complex and are becoming big. To be able to store all the embedding tables, for example, in case of recommendation, or all the weights and the activations, you need to have a large capacity so that you don't have to move data from the host time and again, which is essentially a huge performance bottleneck. Also, the cards need to have on-die memory to be able to efficiently hold all these weights and activations so that we don't have to do many off-chip memory accesses, which is detrimental to the performance as well as power. Next, the memory bandwidth requirement, especially in workloads like recommendation. Solutions have to be able to efficiently handle both the dense compute as well as the large sparse memory accesses to off-chip memory, because memory bandwidth is needed for performance because these memory accesses have long latencies and could critically become a performance bottleneck. Final requirement is the programmability. Because the machine learning workloads are usually rapidly evolving, fixed function hardwares can quickly become obsolete. So the use of more general purpose programmable solutions is highly recommended. Esperanto decided to go with the RISC-V instruction set as the foundation for the design of our ET-Minion course, purely because it's general purpose and it offers a much more robust programmable solution. I'd like to now talk about Esperanto's approach for accelerating these machine learning applications and why we think that this approach is better. Most of the solutions end up using one giant hot chip, which essentially consumes pretty much all the available power budget. Esperanto's approach is to use multiple low-power chips, which essentially still put together would fit inside the power budget. There are a limited number of pins that we can practically put on a single chip package. And if you want to go wide in order to get more capacity or bandwidth, this could be a huge limiter. Esperanto's approach is to distribute the processing as well as the IOs across multiple chips. And as the number of chips scale, the number of IO pins can scale linearly, the capacity can scale linearly, the bandwidth can scale linearly. Hence, you can get more performance at the low power solution. Most of the current chip solutions, or the solutions, they use systolic array multipliers as a compute engine for these AI workloads. And these systolic array multipliers or fixed function hardwares, they do very well on dense computations, like CNN. And you could get a great score on an application like ResNet. But depending overtly on these fixed function accelerators can be limiting in terms of the flexibility that it can offer, especially when you look at models like recommendation, which have requirements for sparse memory accesses. Esperanto avoids this over-specialization by using thousands of RISC-V cores. as the basis for its computation. RISC-V provides a general-purpose solution, a general-purpose instruction set, and we have added a number of vector and tensor units to each of these cores to further speed up the number of arithmetic operations that can be done per cycle. The result is a far more flexible, programmable solution. In addition, it gives the option of having thousands of threads to mitigate the issue of long latency to all these sparse accesses. Next, on a chip which has only a handful of CPU cores, when a model does not fit on the fixed function hardware, then it becomes also an issue with regards to how much parallelism you can get. In case of Esperanto, the full parallelism of all the 1,000 cores is always available for performance. Next, these single chip solutions typically would push for operating at the highest voltage to get the maximum frequency, and this comes at a power cost. Esperanto realized that the transistors, especially the 7-nanometer FinFETs, they operate at the highest energy efficiency when operated at the lowest possible voltage. And we take advantage of this low voltage operations by introducing and having created a lot of circuit level innovations and improvements to the architecture of the base RISC-V cores for our ET-Minion designs. This is a good one. So let me show you an experiment we did that demonstrates the value of this low power, or operating at these low voltages. Here's a graph which shows the energy efficiency of 1,088 ET-Minion cores running our internal recommendation benchmark at all these different operating voltages. For the purposes of this experiment, we model each of our cores to be resynthesized at each of these operating voltage points. Typically, the approach would be to go and operate at the highest possible voltage for maximum frequency. If we did that, our one chip would consume 275 watts of power, which is way over the limit or the power budget available. If we reduce the voltage down to the nominal voltage, which at 7 nanometers is 0.75 volts, one chip consumes 164 watts, which is still higher than the available power budget. If we bring down the voltage further to be able to fit one chip to work under the power budget of 120 watts, we'll have to operate at a voltage of 0.675 volts, and it consumes 118 watts. We fit one chip, but all the power is consumed just by one chip. We want to have a solution which can enable multiple chips to be operating in parallel. So we decided we go to the point in this graph which has the best energy efficiency. It is close to like 0.3 volts. And at this point, one chip consumes around 8.5 watts. So 6 chips would consume 51 watts, which is way below the power budget with a lot of room to spare. At this operating voltage, 6 chips perform 2.5x better than if we were to operate at 118 volts, or at a point which is the nominal voltage, and almost 20x more energy efficient than if we were to operate at the highest voltage. But now we have room in terms of the power budget that can be used. So we decided to go down this curve, increase the voltage a little bit, and operate at close to 0.4 volts. At this voltage, each chip consumes 20 watt, 6 chips consume 120, which fits in the power budget, but we can get 4x better performance, which we recorded for our recommendation benchmark. And the sweet spot that we have observed is anywhere between 0.3 volts and 0.5 volts. So low voltage operation is a key differentiator for Esperanto's ET-Minion design. Now let's see how we put together our entire chip, starting with the ET-Minion, which is shown in this block diagram. The ET-Minion is a proprietary custom-built RISC-V processor, which is compatible with the RISC-V integer instruction set. We have introduced many architectural and circuit optimization to enable low-voltage operations. Shown here in yellow is the RISC-V integer pipeline. The integer pipeline is an in-order core, where each pipeline is further optimized for fewer gates, so that we can enable frequency when operated at low voltages. Each of this core is multi-threaded with two hardware threads for execution, and also has a private SRAM, which the software can configure to be used either as an L1 cache or an L1 scratch pad. Esperanto has added its own vector and tensor unit to each of the cores, optimized for common machine learning applications. The vector tensor unit is optimized for 8-bit integer, 16-bit floating point, and 32-bit floating point, which are the most common data types in the machine learning workloads. The floating point tensor unit, which is shown here in the dark green box, is 256-bit wide, and it can produce either 16 32-bit single precision operations per cycle, or 32 16-bit half precision operations per cycle. The block shown in violet is our int8 tensor unit, which is 512 bits wide and can produce 128 int8 operations per cycle. Esperanto has also added several new tensor instructions, because in these applications, a large percentage of the execution time is spent operating on tensors. These tensor instructions are used for data movement, for compute, and it essentially increases the execution efficiency of our engines. We also have support for transcendental instructions, and typically the ET-Minions operate anywhere between 0.5 gigahertz and 1.5 gigahertz. Moving on to the concept of the neighborhood, the physical design is an important aspect when we consider a complex chip which has over 1,000 cores. We had to do several architectural and physical design improvements in order to utilize the proximity of these 8 cores. So we clubbed together or grouped together these 8 minion cores to form what we call a neighborhood. So 8 neighborhoods, 8 cores form one neighborhood, and 8 of these cores essentially cooperate with each other, both for instruction as well as the data. For example, 8 of these cores can have a single instruction cache that they share. For these highly parallel codes, it's a much better solution than having each core have its individual private cache with redundant copies of the same code. This essentially saves a lot of fetch bandwidth. Another example is cooperating in terms of the data. These applications typically have 3D matrix multiplication, where the data used for compute is pretty much common. So the software can take advantage of this and has added a cooperator feature whereby one core can do a load, 5 minutes. One instruction can do a load from the L2 and essentially serve all the 8 minions with the same data that is required. In interest of time, I'll speed through it. This is a minion shire. We put together 4 groups of these neighborhoods together with 4 megabytes of memory in order to create one minion shire. These shires are connected through a mesh network. All the blocks, except for the SRAMs, they operate on a low voltage plane. To achieve better synchronization and effective synchronization, we have added extensions like fast local barriers and fast credit counters, which we'll talk if time permits. Again, the full chip view, we have 34 of these minion shards put together, which holds 1,088 of our ET-Minions, which forms the compute engine of our design. On the right, we have, on the right top, we have Maxine Shire, which has 4 out-of-order high-performance RISC-V cores. Also a support for PCI Gen 4. And on the left and right, we have a total of 8 memory shares, which hold the LPDDR4X memory controller. Now coming to the extensions. Esperanto added some very key extensions, both vector and tensors, because we developed our extensions before the RISC-V vector spec was ready. These instructions are work in a complementary fashion with our structures that we've defined, like register file and the cache hierarchy and the scratchpad hierarchy, to give the software full freedom to be able to overlap all the work, as well as aggressively pipeline. These extensions support all the known data types, int8, int32, int8, FP16, FP32 for tensor ops, int32, FP32 for the vector ops. We support bfloat16, but just as a storage format, the computation is still done in FP32. So these are the main classifications. We implement a full complement of the RISC-V vector operations. We have specialized tensor operations which are optimized for the machine learning applications. We have features like interleave and transport when we bring in data from the L2 cache to the L1 cache. We have reduction operations, transform operations. In addition to it, we have some cache ops, which helps moving the data from a specific source to a specific destination across our entire hierarchy. We could reserve lines in the scratchpad. We have features to unlock some of the cache lines, which we think are useful and dictated by the software. Typical operations that is performed in ML applications: 2-dimensional matrix multiply and 3-dimensional tensor multiply. Let me quickly go over how we move the data around our chip using our tensor instructions. The tensor load L2 scratchpad is an instruction that moves data from memory into our local scratchpad. Also, an extension is there which moves data from scratchpad to scratchpad, that is minion shire to minion shire. Once the data is available in the scratchpad, we have an instruction called the tensor load, which loads data into a private minion's scratchpad to be used for computation. So the matrix, both matrices A and B that is used for computations are loaded by this instruction. This instruction could interleave and bring the data, transpose and bring the data based on the application needs. Finally, we have the tensor FMA, both processing int8 operations or FP16, FP32 operations, which takes the data loaded by the tensor load from either the scratchpad or from the streaming buffer and does the compute and outputs the result into the vector register file. This just shows a tensor FMA instruction which operates on half precision data. It's a typical A times B producing a value of C. We could use the results, prior results stored in C. It's a feature. We operate on a maximum tile size of 16 by 32 by 16 in case of the half precision. Typically, one such instruction can run for 512 cycles and can produce close to 16K floating point operations per instruction. The integer variant is similar. It runs for about 256 cycles. Again, the maximum tile size is 16 by 64 by 16, but any size of tensor could be used. It runs for 256 cycles and produces up to 32K int8 ops per instruction. There's a quick summary of our synchronization instructions. Since we have over 1,000 cores, it's super crucial for us to be able to effectively manage and coordinate the operations or the execution flow on all these cores. We have two specialized instructions called the barriers and the credit counters with some special registers at both the minion level as well as at the minion shire level, which we can use in order to coordinate the flow through these instructions. A quick view of the software development. We are a RISC-V partner, and we're compliant with RISC-V. We actively coordinate as well as contribute to the RISC-V environment on the left. On the right, we have our own software development and tool suite. We support all the major, I'm almost done, all the major frameworks like GLOW, TVM, and our engine, the RISC-V engine, is general purpose, so any general purpose code can be run through the C++ front end. We have support for common backend LLVM support, and also runtime software with several optimizations included for machine learning. And we also have our own development suites. Esperanto is heavily investing in its software and tool solution and positively contributing to the RISC-V software ecosystem. This is a summary. Low power is extremely important to get a very highly energy efficient solution for these critical ML inferencing applications. Esperanto's innovative vector and tensor units have enabled to accelerate these machine learning workloads by consuming minimum power, minimum area, and giving the highest performance. Our design is very scalable and modular, so we can run applications from the data center to the edge. Thank you very much. Sorry, I was a bit rushed.
Round of applause, please. Jayesh, there were a lot of great questions in the virtual session, so I only am going to ask one question, which is how can people reach out to you more on questions that they may have? Is there a way they can get in contact with you that you'd be willing to share here?
Sure. They can reach me in the Esperanto email.
Okay.
jayesh.iyer@esperantotech.com.
Okay, excellent. So please reach out to him with the questions. Thank you very much. Outstanding presentation. Really made us think. Thank you.
Thank you so much.